Good morning. Today we will start the new chapter Semiconductors and Electronics. This will be our last chapter, and as the name of the chapter suggests, here we will be discussing in details the properties of semiconductors and how with the development of semiconductors or discovery of semiconductors, we invented many devices and a branch of physics called electronics was developed. So before going into the devices, let us see what are the properties at the atomic level or subatomic level that make some materials semiconductors. So let us go into the model of an atom. So here what you can see is the Bose atom model. According to that, we have the nucleus in the center and electrons are revolving around the nucleus in circular energy levels or fixed energy levels. So here you can see different orbits, and you must have learned in chemistry as well that the innermost shell or energy level is called K. It can contain 2 electrons. So this is the first energy level. Then you have the second energy level, usually called the L shell, having 8 electrons. Then we have the M shell, which is having 18 electrons, which can have up to a maximum of 18 electrons, and so on. So these are called the first energy level, which is the innermost, then the second energy level as we go out, third energy level, fourth energy level, etc. And also, as explained by Bohr, when the atoms are heated up, or when some external radiation is incident on the atom, the electrons can absorb energy. If the energy absorbed by the electron is equal to the difference in energy between the levels, they will jump to a higher energy level. Here you can see if a radiation of frequency nu having energy h nu is incident, the electron can absorb that energy and jump to a higher energy level. This is shown here. So the electron is jumping from one energy level to second energy level. So as we go out of the nucleus, as the distance from the nucleus increases, the energy of the levels also increases. So the atoms contain electrons which can jump to higher energy levels by absorbing a radiation. Also, they cannot stay in that higher energy level for a long time. So what happens is they will come down, they will jump back to their lower energy level, and then when they jump back, they will give out a radiation. Here you can see different radiations or different jumping of electrons from higher energy level to lower energy level, and they will give out many radiations. So these series of radiations is called the spectrum. Here is shown the hydrogen spectrum or the electron transitions for the hydrogen atom. So here we have the lowermost energy level, n is equal to 1. Then above that you have n is equal to 2, n equal to 3, n equal to 4, like that higher energy levels. Now, when all the electrons coming down to the lower energy level give out radiations, those series of radiations are called Lyman series. Now, all the radiations that come down to a second energy level is called the Balmer series. And all the electrons that come down to the third energy level gives Paschen series, like that. So these series of radiations given out by a particular atom will be the characteristic of that atom. It's like the fingerprint of an atom. So looking at this range of radiations given out by an atom, we can identify which atom that is. So what I want to focus here is that when an atom is individual, or when we have gas or liquids, the atoms are existing almost in a free way. So they have specific or fixed energy levels where the electrons remain. So these are all energy levels in an individual atom or atoms in gas where they are free. All the electrons are existing in individual energy states. Is that clear to you?
Can you repeat this, teacher, again?
That if a
When an atom in
if the atom is free, for example, in gas, the atoms are widely spaced, that they are free. So in an atom, the electrons are influenced only by the nucleus of that particular atom. So the electrons exist in specific or fixed energy levels. And between that levels, they can jump, absorbing energy if they are jumping to a higher energy level, and coming down to a lower energy level, they will be emitting radiations. So there exist energy levels in atoms which are fixed, and the electrons can jump between them. That's what I want to tell you. Is that clear?
yes, teacher.
Okay, now let us see what happens when atom goes to a solid state. So this is an individual atom. As we saw earlier, the electrons are existing in single or fixed energy state. So when you draw a graph between the energy of the levels, you can draw it as single line, single energy level. The lowest level have a particular energy, which is minus 13.6 electron volt. When you go to a higher energy level, you have a single energy level. So this is the case of an individual atom. They have discrete energy levels or energy states. Suppose when an atom becomes a part of a solid. So in solids, you know that all these atoms are staying very close to each other. So the atoms are very close to each other. So the electrons in an atom is not only influenced by the nucleus of that particular atom. It will be pulled by the nucleus of the neighboring atoms, and they will be pushed by the electrons of the neighboring atoms. So they are influenced not only by the nucleus of their own atom, they are influenced by the nucleus and electrons of neighboring atoms as well. So this is the case when an individual atom becomes a part of a solid, where there are around 10 raised to 23 atoms per unit volume. So per cubic meter, there will be 10 raised to 23 atoms, too many atoms. And they are very closely spaced. So they will be influenced. The electrons in one atom will be influenced by the nucleus and electrons of neighboring atoms. So different electrons in the energy level. For example, if we consider this atom as A, the neighboring one as B, then the electron in the first state or the innermost state or energy level will have a slightly different energy from the similar atom's electron, which is in the first state, because they are pulled and pushed by neighboring atoms, right? So they do not have a fixed energy level. Instead, they may have slightly varying energy levels. So you cannot express that as a single energy state. You will have to express them as a range of energies or a band. Okay, let us read this. When atoms are included in a solid material, then the electrons of the same orbit do not have the same amount of energy. Why? The atom in a solid is greatly influenced by the closely packed neighboring atoms. So, the electrons in any orbit of such an atom can have a range of energies rather than a single energy. So the range between the electrons of maximum energy and the minimum energy at the same orbit is called the energy band. So if you look here, this is the energy, the maximum energy that an electron in that range can have, the uppermost, and this is the least energy that the energy in the first state or first energy level can have. So this range is called the energy band. So when an atom, instead of staying individually, comes to a solid, what they have is a range of energies. Even if they are in the same level or same energy level, different atoms and different electrons in different atoms will have different, slightly different energies. So you cannot express them as single state with a number, but you have to give them a range of possible energies. Is that clear? What is an energy band? How an energy band is formed when from individual atom it goes to a solid state, a crystal. Is it clear?
Yes, teacher.
Okay. So if you are asked what is an energy band, you will have to tell the range between the electrons of maximum energy and minimum energy at the same orbit is called the energy band. And if you are asked for two questions, explain how energy bands are formed in solids, you will have to tell all these points, that when atoms are included in a solid material, then the electrons of the same orbit do not have the same amount of energy. And this is because atom in a solid is greatly influenced by the closely packed neighboring atoms. So the electrons in any orbit of such an atom can have a range of energies rather than a single energy. So this is the explanation why or how in a solid, there exists energy bands instead of energy states. Now, let us see more about energy band. What are the different types of energy bands? There are different energy bands like different energy states, but we will focus more on three particular energy bands or two particular and the gap between them. So you have the valence band, conduction band, and forbidden band. Let us see what are they. Now, here, if the atoms are free, they have energy levels or states. So as the energy increases, as we go up, the energy levels are shown by single lines. But when we come to a solid, because of the influence of the neighboring atoms, we cannot express them as single state. We will express them as bands. See the bands. See, the width of the band increases as we go up, or the energy range increases as we go up. We know that as we go out of the nucleus, the electrons are more free from that particular atom's nucleus and will be influenced more by the neighboring atoms. So that is why as we go up, the width of the energy bands are increased. Now we have many lower energy bands, but in particular, we are going to see what is meant by a valence band, what is meant by a conduction band, and what are forbidden bands. You know what are valence electrons, right? The electrons in the outermost orbit of an atom are the valence electrons. Now, the range of energies of the valence electrons is the valence band. So, all the electrons which are in the outermost shell of an atom are called valence electrons. So, if you see the previous ones, these 1, 2, 3, 4, 5, 6, these 6 electrons are the valence electrons because they are in the outermost shell or outermost level. Okay, now the range of energies of the valence electrons or the outermost electrons is called the valence band. So valence band means the outermost energy band in an atom. Now, what is outer to valence band? Let us see that. For inert gases, the valence band is filled and cannot accept more electrons. Why for inert gases the valence band is filled? What are inert gases or noble gases? You must have some idea about inert gases or noble gases. What are they? What are inert gases? Inert means not entering into a chemical reaction. So noble gases or inert gases have in their outermost shell or the valence shell 8 electrons. So 8 electrons is the maximum they can have and they cannot accept more electrons. So they are full. So for inert gases, we can say that the valence band is filled. No more electrons can be accepted. But in other materials, the valence band is partially filled. For example, if an atom have only 5 electrons in its outermost shell, it can have 3 more extra electrons. So the valence band is partially filled and therefore they can accept more electrons. Now, if an atom has only 4 electrons in its outermost shell, can you tell me whether its valence band is completely filled or partially filled? If the valence band is partially filled, how many more electrons it can have?
4.
Yeah, it can have 4 more electrons. So that is what is a valence band. It's nothing but the valence shell. Now, when it comes to a solid state, we call it valence band. Now, the free electrons in an atom take part in conduction of electricity. This happens especially in metals. We know that in metals, the outermost electrons are so away from the nucleus that they are almost free. And as soon as we apply some voltage, they are free to conduct electricity. So these electrons are called free electrons. So these free electrons in an atom take part in the conduction of electricity. So these electrons are called conduction electrons. And the range of energies of the conduction electrons is called the conduction band. See, for the conduction band, the energy is higher than the valence band. So those electrons which are in the outermost shell, but even free to conduct electricity, which means they can freely move away from the bonding of the atom, which are free to conduct electrons, they belong to the conduction band. So all materials will not have electrons in the conduction band, but some materials which can conduct electricity will have electrons in the conduction band. So let me ask you one question. If I take a piece of plastic, a fiber, will it have electrons in the conduction band? Plastic or fiber, will it have electrons in the conduction band? Are there free electrons in plastic? Will a plastic conduct electricity?
No.
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 So are there free electrons in plastics?
No.
So will there be any free electrons in the conduction band of a plastic material?
No.
No. So sometimes the conduction band can be empty, like in a plastic material. No free electrons are there, so nothing will be there in the conduction band. Let me ask you another question. If I take a piece of copper, okay, will there be electrons in the conduction band of copper? Is copper a metal? Yes.
Yes.
Is copper a good conductor of electricity?
Yeah.
Is copper having free electrons then?
Yes.
So, will there be electrons in the conduction band of copper?
Yeah. Yeah.
Yes. So, free electrons are occupied in an energy band which is above the valence band, which is called conduction band. So, the range of energies of the conduction electrons is called the conduction band, which is more than that of the valence band. Okay? The energy
Teacher,
of the, yes.
can you explain the free electrons again?
Free electrons means in metals and all, the outermost energy electrons, the outermost shell electrons or the valence shell electrons, some of them are free to conduct electricity, which means they are not actually tightly bound to the atom of which they are part. Okay, that is why when we apply a small potential for a metal, electricity is conducting because these free electrons can easily move away from their parent atom. Therefore, they are called free electrons. And the existence of these free electrons are the reason why metals conduct electricity. So they are having an energy a little more than the normal valence electrons or the electrons which are having energy in the lower level of the valence band. So those energy band where the free electrons are occurring or are called the conduction band. Is that clear? What are free electrons?
Yes.
Okay, so let us see the last one, which is the forbidden band. What is meant by forbidden? Not allowed. Forbidden means not allowed. So the energy gap between the conduction band and valence band is called the forbidden band. So the or space between the conduction band on the valence band or the energy values in between the conduction band and the valence band, this is called the forbidden. Forbidden means no electrons can have these energy levels. Suppose this energy value is 2 electron volt, and suppose this energy value is 3 electron volt. So if a electron exists, it cannot have an energy value 2.3 electron volt because that value comes in the conduction forbidden band. Is that clear? Suppose this value, I'm just guessing, this value is 2 electron volt, the uppermost of this valence band, and the lowermost of this conduction band. Suppose it is 3 electron volt. So no electron in that material can have any energy in between 3 electron volt and 2 electron volt. So if we say there is an electron having energy 2.5 electron volt, it is not allowed. It doesn't exist. It's forbidden. Is that clear? So that is forbidden band. Okay. Now let me just give you some values which is not correct. I told this is 2 electron volt. I told this is 3 electron volt. I'm telling this is 1 electron volt. A electron having energy 1.5 electron volt. In which band will it lie? A electron having energy 1.5 electron volt. Where will it lie? I told this is 1 electron volt, this is 2 electron volt, this is 3 electron volt. Where will it lie?
The 2 electron
Forbidden band.
The electron having energy 1.5. This is 1, this is 2, this is 3. Electron having energy 1.5 electron volt. Where will it lie? One 1.5 lies between 1 and 2, right? So it is within the valence band. So it will be lying in the valence band. Okay, let me ask you another question. A electron having energy 3.2 electron volt. Where will it lie?
the
Conduction.
It will lie in the conduction band. Above 3 means conduction band. Now another electron having energy 1.8 electron volt. Where will it lie?
valence
Valence
band.
band.
Valence band. Another electron having energy 2.5 electron volt.
Forbidden band.
Conduction.
It will be in the
Valence.
forbidden band means there is no such electron. An electron cannot have 2.5 electron volt. Okay, so 2.5 electron volt, an electron cannot have. So there are no such electrons having energy 2.5. It's forbidden for electron. That energy value will not be there. That is the meaning of forbidden bands. So forbidden bands means that bands are actually not there. Those values of energies the electrons cannot have. Is it clear now?
Yes, teacher.
Okay. So these are the valence band, conduction band, and forbidden band. Now, I hope you know what are insulators, what are conductors, and what are semiconductors. What are insulators? What are insulators?
Free flow of electrons.
It does not let electrons
Yeah,
to
there
flow.
is no free flow of electrons.
There are no flow of electrons or they cannot conduct electricity, right? And what are conductors?
They can conduct electricity.
They can conduct electricity. And what are semiconductors?
There will be resistance.
There will be some resistance. Their resistance will be in between that of conductors and insulators. Now let us see what are conductors, what are insulators, and what are semiconductors, which you have already learned. But here we will focus on how we can classify them according to the arrangement of the valence band, conduction band, and band gap, which is nothing but forbidden band. Okay. So let us see how we can classify materials into conductors, insulators, and semiconductors looking at their energy bands. So the material through which electric current cannot flow are called insulators, which means they have very high specific resistance. Their specific resistance is almost 10 raised to 12 ohm meter. Now, in an insulator, what you have is a valence band which is partially filled. See, in an insulator, this is a valence band which is partially filled, and the conduction band is completely empty. Why the conduction band is completely empty in insulators? Because there are
Because
no free electrons. Yes, tell me why?
Because
there
there
are
are no.
Yeah, there are no free electrons, no electrons available for conduction. So the conduction band is completely empty. And the gap between the conduction band and valence band is very high. See the band gap, the gap between valence band and the conduction band, which we can also call the forbidden gap, is very high. So this value, the band gap, is 6 electron volt to 15 electron volt. So if the band gap is 6 electron volt, if this is 2 electron volt, this value will be 2 plus 6, 8 electron volt. So if an electron have to jump from the valence band to conduction band, they need to get 6 electron volt, which is not possible by just applying a potential difference between them. So the insulators cannot conduct electricity. Even if we apply a potential difference, they cannot give this much energy, that is 6 electron volt to 15 electron volt. So the electron here cannot jump to the conduction band, so they cannot conduct electricity because their band gap is very large. Okay. Now let us consider what are conductors. The materials through which electric current can flow easily are called conductors, as you are aware. And they have very low specific resistance. See, it is only 10 raised to minus 8 ohm meter, their specific resistance. And this is a conductor. So what is the difference you see here and here between an insulator and a conductor? What is the difference you see?
There
They
is
don't
no
have
band
any
gap.
band gap.
There is no band gap. Or you can tell that the valence band is conduction band. That was why I had a difficulty in explaining why the free electrons which are in the valence band and at the same time free and in the conduction band. See, the valence band and conduction band are overlapping in a conductor or in a metal. So the electrons in the uppermost level of the valence band, they are part of the conduction band because they are overlapping. There is no band gap. So most of the electrons which are in the valence band are also in the conduction band. Therefore, they are free and they can conduct electricity. So this is the difference. That is why an insulator cannot conduct electricity while a conductor can conduct electricity. So there is no energy gap between the conduction band and valence band, or they overlap in conductors. That is the case of conductors. Now let us see what is the case of semiconductors. Materials having specific resistance between conductors and insulators are called semiconductors. See, their specific resistance is 10 raised to minus 4 ohm meter. Okay, so you can tell that their specific resistance is in between that of conductors, which is 10 raised to minus 8 ohm meter, and insulators. See, less than that of insulators, more than that of conductors. So these materials are called semiconductors. Now let us see the energy bands in a semiconductor. So what is the difference you see? Is there a band gap for semiconductors?
Yes.
Yes, but they are small. They are not as large as that in insulator, but there exists a small band gap. And the band gap is less than 1.1 electron volt, very small. So usually when we consider pure semiconductors, we often refers to germanium and silicon. For germanium and silicon, their band gap is 1.1 electron volt and 0.7 electron volt. So it is always less than or about 1.1 electron volt. Now, when we apply a small potential difference or even at normal temperature, some electrons will get this 1.1 electron volt either from the applied potential or from the temperature, and there is a chance that they can jump to a higher energy level because the band gap is small. So there will be few electrons available in the conduction band and they can conduct an electric current, but it is very less. The free electrons available are less and their conductivity also will be less. So that's all I want to discuss today in this class. And next class, we will see more about the characteristics of semiconductors, both in terms of the band, energy band and otherwise. Okay, so in this class, what we have discussed is, we have discussed in normal or free atoms, there are energy levels surrounding the nucleus where the electrons can stay. And when they come to a solid, instead of the energy state, it becomes energy bands. Instead of a fixed value for energy, it will come to a range of values which the electron can have in each energy state or energy band. This is because of the influence of the neighboring atoms. Now, we consider different types of energy bands, and especially we focused on the valence band, conduction band, and forbidden band. So you should be able to answer what are valence band, what are conduction band, what is meant by forbidden band. And then you saw how to classify conductors, insulators, and semiconductors using band theory. So you have to know, you must be able to draw a diagram showing the energy bands in insulator, semiconductor, and conductor. Is that clear to you?
Yes.